So 1-2b today. And we're going to do some properties of functions. Properties of functions. And not the kind of properties that you learned in Algebra 2, like distributive property, commutative. We're just going to learn, we're going to do some like, almost like pieces of functions, like what they're doing, how they're reacting in the graph, stuff like that. So we're going to talk about increasing and decreasing intervals. We're going to talk about local and absolute maximum and minimums. We're going to do some symmetry and asymptotes. We got a lot to cover. Here we go, part A. Part A. We're going to do increasing and decreasing. Increasing and decreasing. So we're going to have some functions. And we're going to talk about where this function is increasing, where it's rising, or where it's decreasing, where it's going down. Also, it could be just a constant graph, okay? So let me show you some examples of this so that you kind of have a little bit of an idea about increasing and decreasing. I could have a graph like a basic cubic function. And a cubic function looks like this. Goes like that, okay? And at all points on this graph, if I jump on this graph, here I am on my skateboard. I'm going uphill, because you always read graphs from left to right. And I'm going uphill, and this is constantly increasing as I go. Okay, if I start here at the negative x, here's my y. The next one, my y gets bigger, 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 all the way up from left to right. Okay, so this graph is constantly increasing. We're going to do some studying of exponential equations, and we do some exponential decay, and an exponential decay could look something like this. Okay, so as you're going along left to right, so you're over here in the negative x's, your y's are pretty high. As you're going along, your y's are getting lower and lower and lower, and this graph is constantly decreasing. So you read from left to right. So here I am on my skateboard. I am no longer going uphill. I'm actually going whee, and I'm going down. All right, now those graphs are interesting. They're okay. One's continuously increasing, the other one's continuously decreasing. What about something that kind of changes? How about your basic parabola, right? Here's your basic parabola. Okay, there it is. And this graph is decreasing on this side until you get to 0, and then it increases on that side. So decreasing, and then it increases. Okay? So we would say, for this one, we would say that this graph is decreasing from negative infinity until 0, and then it increases from 0 to infinity. Now, those are intervals of x values. Has nothing to do with the y values when you write the answer, okay? This is right here, from this interval to here on the x's, and then this interval to here on the x's. You always go across this way. You don't even care about up or down. And then you could also have a graph that's constant. Let me show you one of those. Constant graph, those are kind of boring, like y equals 3. Okay, that's neither increasing nor decreasing, so that would be constant from negative infinity to infinity. Okay, so let's do some. Are you ready? Number 1. You'll need your calculator for this, because you're allowed to graph this on your calculator. It's fine. It's going to say find the intervals of increasing, decreasing, or constant. Increasing, decreasing. All right, letter A. We're going to do 2 of these. Let's do f of x equals x plus 2 quantity squared. X plus 2 squared. Maybe some of you know what that looks like without even having to use your calculator, which is great. We're going to do that when we get to lesson 1-3 this week. You'll know how to just picture graphs immediately, okay? So this one right here is a parabola, and it's shifted 2 to the left. And you can graph that on your calculator if you want to. And it looks like that. Okay, so this graph is increasing and it's decreasing. So this graph is increasing. Now remember, these are x values, okay? Not y. Not y. And a lot of people think, oh, I'm going down to 0 on the y. And that's true, but we don't talk about the intervals that way. Intervals are here and there. So this graph is increasing from -2 to infinity. And it's decreasing from -infinity to -2. Let me see. I don't know if the book includes those. Do they? Sometimes books do, sometimes they don't. The last book I had left them as open intervals, and what does this book do? Let me see, hold on. Increasing, decreasing. They actually close the interval. I'm okay either way. Okay, so they would say -2 is included in both of them, which is interesting to me. I'd rather not include them. All right, letter B. Try this one. G of x is equal to x squared over x squared minus 1. All right, you are allowed to graph that on your calculator. That's fine. So we'll do that. We're going to do x squared divided by parentheses. Make sure you put parentheses around x squared minus 1. And then I'm going to hit zoom 6. Okay, I'm going to draw this graph right here for you so that we can talk about it a little bit. So this graph goes like this. And then it's down here like that. And then it does that. Okay. Now, the domain of this is x is everything except for what? 1 and -1. Perfect. That's why right here at -1, there's what's called an asymptote, which we'll discuss. And at +1, there's an asymptote there too. Okay? So this graph is increasing. Let's just read it left to right. This graph is increasing from -infinity to -1. So increasing from -infinity to -1. Nothing's going on at -1 on this graph. And then from -1 until I get to 0 on x, my graph is still increasing. And that's why we don't want to include -1 in this problem, because it's not part of the domain. Maybe that's why they include it in the last one, probably. All right, and then where is this graph decreasing? It's decreasing, so from here, it's decreasing. All my y's are going down, 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 and down. So 0 to -1, or +1, sorry, 0 to 1. And then it's still decreasing from 1 out to infinity. Okay, so those are your intervals of increasing and decreasing. Why do we even care? Why do everyone want to know this? Well, you know, a lot of this is pre-calculus is getting you ready for what? Calculus, right? And there's a lot of stuff in calculus that involves intervals of increasing, decreasing. Okay, let's move on. Part B. Part B, we're going to do some extrema. Such a weird word. I've never liked that word. Extrema. Extrema. When you think about the extreme, that's like the ultimate way out there. Okay, and that's what we're going to do. We're going to talk about maximum and minimums. Max and min. Okay? These are the peaks and valleys of your graph, and it's where your graphs change usually from increasing to decreasing. Usually. Okay? So like, for example, let's say we have this graph and it goes like this. Let's say it's closed there, but let's say it goes forever that way. Okay? And there's some special points on this graph. Okay? This graph is increasing, increasing, increasing until it gets to a point right here. Okay? And that point is a maximum. So if it's increasing on the left and decreasing on the right, it's a maximum of the graph. Now, is that the maximum of the graph? No. It's called a local maximum. Okay? So P is a local max. It's a maximum in its neighborhood. Sometimes they talk about neighborhoods, which is really cute when you think about neighborhoods in a graph. And this guy, he's living on top of the hill and everybody's below him. But there's someone living up higher on the next hill. But in his neighborhood, he's the top guy. Okay? Or girl. Down here in the valley, when your graph is decreasing on the left and increasing on the right, you have a minimum. Let's call it Q. Q is a local minimum. The reason why it's not the absolute minimum of the graph is because this graph will go forever and ever down. So there is no absolute minimum. Okay, it goes to a negative infinity. All right, let's call this one up here. Let's call it R. R is a absolute max. It is the highest point of the graph. It's greater than all of the other y's, okay? That's what it is. The endpoints, we would consider this a local min since it drops down to here, but we're not really too concerned about those, okay? So we're not. Like a lot of times they'll make them keep going and stuff. Okay, so here we go. And we're going to do a lot of this on our calculator. Number 3. We're going to use a calculator to find any local extrema. Local extrema is like all the different maximum, minimums, all of them. Yeah?
Did we do number 2?
Oh, we didn't. Thanks. No, because the last one I did A and B, huh? Oh, what did I just do? Highlighted? I meant to erase.
Thanks.
I know, I'm the same way. I gotcha. All right, number 2. Okay, so let's do f of x equals x to the 4th minus 7x squared plus 6x. And we're going to find any local extrema, maximums, minimums, all that stuff. All right, so I'm going to pause this and do it on start recording again. So we graphed it. It looked like this, went like that, did it dip down there, and up like that, something like that. Okay, and we found this point using the calculator doing the minimum, and we got that, and that's an absolute minimum, by the way. It's the smallest y value you're going to find on this graph. And you can write it as a point, negative 2.06, negative 24.06. Okay, a lot of people will write the maximums and minimums as just y values, and that's okay too. Never write it as just an x value, though. Okay. And then we need to find the next one. And the next one, it looks like there's a peak right here. And if you can't see that, you might want to zoom in. You can actually hit the zoom in button. Oh, mine didn't work. Mine zoomed in on the other one. Zoom 6 might be a little bit better to kind of zero in on that point now. Yeah, there is one. So now we're going to calculate the maximum. So go second trace, calculate the maximum, and you want to be on the left-hand side. So I hit enter on the left, enter on the right, and it'll find that maximum is at, this is just a relative maximum or local maximum, and that maximum's at point, let's just round to 1 decimal place. 0.5, 1.3. Okay. And then there's another minimum coming up, a local minimum, where it dips back down. So I want to calculate the minimum again, number 3. Go to the left-hand side, hit enter. Go to the right-hand side of it, hit enter. And that is a local min at 1.6, negative 1.8. Okay. Now, if I asked you to tell me where this graph is increasing or decreasing, you'd have to know these points, these x values. This graph is decreasing from negative infinity until you get to what x value? Negative 2.06. And then it increases from negative 2.06 until you get to 0. These are intervals of x, okay? And then, it, then it, then, 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 to 1.6, and then it increases from 1.6 to infinity. So finding the maximum minimums are really helpful in finding the increasing and decreasing values of the graph. Okay? And increasing and decreasing are always the x values. All right, got some more time. Part C. Halfway done. Are you going to make it, Anthony? Are you going to sleep? You okay? You have a good weekend?
Yeah, I saved all my homework for last night.
Oh, I know some of my last class, I didn't go to bed till after midnight last night. Symmetry. Symmetry. Alrighty, so we're going to have two important types of symmetry. They give you three, but there's really two that are important. I'm going to talk about the first two. If you have a graph, so symmetry number one, if you have a graph that is symmetric over the y-axis. Symmetry means that you can take your paper and fold it, and it's going to be exactly the same on either side when you fold it. You learned symmetry in, I think probably in geometry, did some symmetry. Okay, so y-axis. Now, symmetry, if it's over the y-axis, these are going to be our even functions. Functions can be either even, odd, or neither. Even functions are symmetric over the y-axis. Even functions are interesting. So if you have f of negative x, it will equal the same thing as f of x. Okay? For example, let me give you the most basic even function there is. Are you thinking of a function that's symmetric over the y-axis? The most basic of them all? Yes, perfect. Y equals x squared, a parabola. Okay? And it's not because this exponent is even, because I could have x squared and then do a x minus 2. Remember that graph we just did? And that's not symmetric over the y-axis because it's shifted to the left. But this is just a regular parabola. And watch, if I plug in x equals negative 3 and x equals positive 3, they're exactly the same y value. Okay? So if I do f of negative 3, I get 9. And I do f of positive 3, I get 9. And these are exactly the same. This is an even function for all values. For all values. Okay? You can do it two ways. You can either show that something is even algebraically by plugging in negative x, or you can show it graphically by showing that it's symmetric over the y-axis. All right, number two. The second type of symmetry is symmetric over the origin. The origin is the point 0, 0. If it's symmetric over the origin, then what you have is an odd function. Okay? Odd function. Now, for odd functions, if you plug in f of negative x, you will get the opposite as your return answer for f of x. Okay? Let me show you the most basic odd function there is. It's the graph y equals x cubed. It goes through 0, 0, sorry. Okay, this is symmetric. I don't like that graph at all. It's symmetric over the, ew, that's even worse. Sorry. It's symmetric over the origin. In other words, if I pick the point x equals 3, I get 27. But if I pick x equals negative 3, I get the opposite. I get negative 27. So these end up being opposite. So if your points are exactly the same, no matter you plug in a positive or a negative x value, it's even. If they're exactly the opposite, when you plug in 3 or negative 3, it's an odd function, opposite for odd. Okay, the third type of symmetry, I don't even know if I really want to talk about it. It's over the x-axis, and those aren't functions unless, did you get that one right in the homework? Y equals 0 is the only function. It's a function. Yeah, that one was weird. But. Okay, so here we go. Let's do some. What number are we on? 3? 3. Number 3, we're going to check for symmetry. Check for symmetry. You may use your calculator. I have no problem with that. I'll show you both ways. Letter A, f of x equals x squared minus 3. F of x equals x squared minus 3. So there's a couple ways you can do this. One, you go to your calculator and you graph it, and you can basically just look at it. This is a parabola that's been shifted down 3. When you graph it, you get that. And you can just ask yourself, okay, how is this symmetric? Well, it's definitely symmetric over the y-axis. If I cut my y-axis in half and fold my paper over, it'll be exactly the same. All the points will land on each other. So this is symmetric over the y-axis. It's an even function, so on and so on. Okay, you can also do it algebraically. So let's say I didn't let you have your calculator, or your calculator malfunctioned. Ooh, who's taking the ACT this weekend? Anybody? Speaking of calculator malfunction, hopefully it doesn't happen. Because that's scary. All right, if you plug in negative x into this function right here, you would get negative x squared minus 3. And what would happen? X squared minus 3. Guess what? That's exactly the same thing as f of x. F of x and f of negative x are equal to each other, and so it's even. It's more of a proof that way than just a graph and saying, oh, it's symmetric, you know? Let's try another one, B. Let's do h of x is equal to x cubed over 4 minus x squared. Now this one's pretty intense here. Let's graph this on our calculator and see what happens. Pause it. So if you graph it, you look at it, symmetric over the origin. Let's do that thing, I don't know what that is. Let's do the thing where you plug it in and do it algebraically, okay? So let's find out what h of negative x is. I would do negative x to the third over 4 minus negative x squared. Okay, supposing I didn't let you have your calculator, this is the way you'd have to do it. Negative x to the third is negative x to the third. Negative x squared is still negative x squared, and you think, well, those aren't opposite, but they are. This negative, you can pull out to the front, right? You don't want a negative over a negative. That makes a positive. This actually is the opposite. You pull that negative out to the front. Everything stays the same. And what you get is you get the exact opposite function than you started with. These are opposites. This is positive x cubed over 4 minus x squared, and this is the negative x cubed over 4 minus x squared. They're opposite. Opposite, what happened there? Opposite is odd, symmetric over the origin. Ooh, those are all O's. Wow, I've been teaching this for 100 years, and I just realized that. Maybe not 100. It feels like it, though, some days. It feels that way. Okay, last part. Letter D. Asymptotes. Asymptotes come in all shapes and sizes. There's some fat asymptotes. There's some thick asymptotes. There's, you guys laugh at none of my jokes. You guys all suck. -5 for the entire class. Lighten up, people. This class isn't that bad. My other class, they just crack up. You should go in there. It's much more fun in that room. This room's very serious. You guys are all try hard. You're a bit extra. The other class, they're like, oh, let's have some math. This is fun.
What's your test average?
Yeah, you guys are better. You're tryhards. Yes. You're better mathematically than they are. They're more fun though, okay? So we gotta balance this out. We gotta do some mixing. We need fun and good at math. Oh my gosh, I just described myself. Okay, here we go. Number 4. Asymptotes. Okay, I'm gonna let you use your calculator for this. We will do asymptotes next chapter and we'll really focus on them a lot. Right now we're just using our calculator. So there are 2 different types of asymptotes that we're gonna do right now. There's more than that, but we're gonna do horizontal and vertical. Horizontal and vertical asymptotes, okay? So I think we only have time for one more question. Number 5, I think. Oh, me too. So tired. All right, f of x equals 2x squared over 4 minus x squared. So we're looking for the vertical and horizontal asymptotes. Asymptotes are the parts of the graph where your graph kind of glides right along. You've studied asymptotes a little bit last year in Algebra 2 when we did, what was it, like exponential graphs and stuff like that. All right, so I'm going to put parentheses around 2x squared. I'm going to divide it by parentheses 4 minus x squared. I think we've seen this graph already today. Oh, yeah. We kind of did. A lot like it. Okay, so there's some asymptotes here. My vertical asymptotes are going to be where this graph kind of, takes an infinite discontinuity. So my vertical asymptotes are at x equals, vertical is always x equals plus or minus 2. And that makes sense because look at this. Look at the domain. Can x be 2 or negative 2? No, cannot. It makes 0 in the denominator. Horizontal asymptote's a little harder to find. Horizontal asymptotes is y equals a number. And the way that you can do this right now is you can hit trace and trace it out, or you can go to the table and just see where's y going. Okay, it's pretty obvious. So I'm not going to trick you. It's not all of a sudden going to jump underneath negative 2. Do you see that? I'm going way out there. It's not changing. 90. Or you could also go the other way. Okay, if you go the other way, it's still negative 2. So y equals negative 2 is the horizontal asymptote. And later on, we're going to do a little bit of limits type of thing where you will see why it is negative 2. Right now, we're just looking at our calculator and trying to estimate it. Okay? All right, I spoke to the bell.